Hey students, in this video we're going to talk about tangent planes. So a tangent plane is something like this. So imagine good old Mr. Moore comes along and draws a plane out in space. So this is a plane. And then like in contact with that plane at like one point, we'll draw beneath it. So then I have this surface. And the surface is again in 3 dimensions. So like that point right here is where the plane intersects the surface. This is a tangent plane. It touches the surface at exactly one point. The equation for the plane is we need a partial derivative for every variable, and we want to evaluate the derivative at that point. In section 12.6, we discovered that that was the gradient at that point. And so then if we take that and the vector that comes from some arbitrary point and the point that we're trying to find the equation of the plane at and do the dot product, we end up with a plane because remember, dot product and this vector are going to be orthogonal. They intersect at a 90-degree angle. So the equation that we get from this is f of the partial derivative evaluated at the point times, again, this x minus x0 really is a vector. This is a vector. All of these things that I'm putting braces under are not technically, they are vectors. It's just that x, y, and z are arbitrary points, and so they're going to make a vector. And so to do this, all we need is partial derivatives and to evaluate each partial derivative at the point. So for example 1, we have this equation, f of xyz equals xyz minus 12. So the partial derivative at x is just yz. And at the point, and so we'll say then fx of -2, 3 is -2 times 3, which is -6. Then we need the partial derivative at y, which is xz, and the partial derivative at y evaluated at -2, 3 is -2 times 3 as well, which is also -6. Lastly, we need the partial derivative at z, which is x, y, and then fz evaluated at -2. -2 is -2 times -2, which equals 4. So the equation of our plane we'll put over here. So we'll say for the plane, we get -6 times x minus -2 minus 6 times y minus -2 plus 4 times z minus 3 equals 0. So now for my purposes, that's good enough. But on a multiple choice test or something, you may see this go farther. So this is x plus 2. So that's really -6x minus 12 minus 6y minus 12 plus 4z minus 12 equals 0. So now if we, I don't know, move all of the variables to the right side, for instance, we'll get -36 equals 6x plus 6y minus 4z. And we could divide everything by 2, but let's not, and say that this is the equation of our plane. Now, one thing to check is you should substitute in x, y, and z to see if you get this value. If so, you haven't messed up any algebra steps. If you don't, go back and check your algebra. For the second example, we want to find the equation of a plane tangent to f, x, y, z at y equals ln xz squared minus 2 at the point e2 and 1. So we still need our partial derivatives. So the partial derivative at x is, so y is going to be a constant. We multiply that by the derivative of ln xz squared, which is z squared divided by x z squared, which turns out to just be y over x. And we're going to say, we're going to evaluate that at the point e to 1 is going to equal, y is 2, e is 1, so this is going to be 2 over e. And then fy is, so y is the variable, the derivative of y is 1 times its constant, which is the ln of x z squared. And then we evaluate this at e to 1. That's going to be the ln of e times 1 squared, which is 1. The ln of e is 1. And then our partial derivative at z is y is a constant multiplied by the derivative of ln xz squared, which this time is 2xz divided by xz squared, which we end up with the x's canceling, and we get 2y over z, so 2y over z, and we evaluate this at the point e to 1, and we're going to get 2 times 2 divided by 1, so 4. The equation of our plane is 2 over e times x minus e plus 1 times y minus 2 plus 4 times z minus 1 equals 0. For this one, because of the 2 over e, we're not going, actually you could distribute. So we get, the 2 over e is just a constant. So we're going to get 2 over ex minus 2 over e times e is just negative 2 plus y minus 2 plus 4z minus 4 equals 0. So that's going to mean that we get 2 over ex plus y plus 4z equals, what's that, 8? All right. That's kind of it. So from Calc 1 and Calc 2, we learned respectively that a first degree Taylor polynomial or a linear approximation can be written as the product of the differential times the partial derivative, or times the derivative at that point. Using this same principle but doing points in space, we can approximate, what we're approximating is how high above or how low below the XY plane we are given a particular point, and using that plane to approximate that point in space. So what that's going to mean is that this part, this x minus a is, this is our delta x, and this y minus b is our delta y, and this f of ab is our known z value. And so the partial derivative evaluated at that point at x, so the partial derivative of x evaluated at the point times this differential plus the partial derivative of y times this differential, evaluated at that point, plus the known value, is going to tell us how much up or down our z value moves. So this entire calculation is the change in z. So if we take our known value of z and add the change to it, we are approximating a new value of z. So this is a linear approximation. I guess you could call it a planar approximation in some regards. So all we're doing is taking a fixed value and adding to it a shift in 3 dimensions, really, because it's going to move up and down or left and right. So again, keep track of this. X minus a is delta x and y minus b is delta y. That's going to come up in example 4. So for example 3, first change is make this 1.05. I don't know why I have 5. I was going crazy. So that should be 1.05. But we want to use this to approximate, we want to use the function f of xy equals xy plus x minus y and the point 4y to approximate the point 4.1 and 1.05. Or the point 4.1 and 1.05. So we need the partial derivative for x, which is y plus 1. And if we evaluate this at the point 4, 1, that's going to give us 2. And then fy is going to equal x minus 1, which we evaluate at the point 4, 1, and we get 3. Now, according to this, we also need the point f of 4, 1, which is, 4 times 1 plus 4 minus 1. That's 8 minus 1, which is 7. So what we know, all right, so like, imagine we're out in space at the point 4, 1, 7. What we're trying to find is what's the z coordinate at 4.1, 1.05. That's one way to think about it. So what we expect is if the partial derivative for x is positive and the partial derivative for y is positive, we expect our z to go up a little bit. Now, how much does it go up? Well, we take the partial derivative for x. So we're going to have, first, let's write a function for this. So we're going to have, to approximate points close to 4, 1. That's what the LXY means. We're approximating points close to that. So that's going to equal our slope at x. So 2 times x minus 4 plus 3 times y minus 1 plus our known z value of 7. So now again, if we shift x to the right a little bit and y up a little bit, we expect our z to increase a little bit because both of our slopes are positive. So L of 4.1, 1.05 is equal to, remember when I told you that the x minus a is our delta x and the y minus b is our delta y. So 4.1 minus 4, that's just 0.1. So 0.1 plus 3 times 1.05 minus 1 is 0.05 plus 7. And so that's going to equal 0.2 plus 0.15 plus 7, which is 7.35. But what we're really saying is that from this point 417, if you change x and y by 0.1 and 0.5 respectively, you expect the z to go up to 0.735. So this is our 0.35. This is our delta z. That is our delta z. And so that's what we're going to find on example 4 is given a function and a change in X and Y, how much do we expect Z to change by? So for example, 4, what we're approximating is a shift from, we're expecting, like, what we're asking is, what's the change in Z if X changes from 1 to 1.2? Here, delta X is equal to 0.2, and then Y changes from 3 to 2.5, which means that delta Y is equal to negative 0.05. So what we know is delta Z is going to equal the partial derivative at X times delta X plus the partial derivative at Y evaluated at a point times delta Y. So our partial derivative for X is 2 minus 2Y. And if we evaluate this at the point, 1, 3, we're going to get 2 minus 6, which is negative 4. And then our partial derivative for Y is negative 3 minus 2x, which if we evaluate at the point 1, 3, is negative 3 minus 2 is negative 5. So according to our formula, we already know our delta X and our delta Y. So what we're saying is delta Z is going to equal negative 4 times delta X, which is 0.2, plus Fy, which is plus negative 5, times delta Y, which is negative 0.5. So what's that? Negative point, let's say negative 0. All right, start that over, guy. So what we get is negative 0.8, and then minus 2.5, which is negative 3.3. So what we expect is our Z to go down negative 3.3 when X changes by 0.2 and Y changes by negative 0.5. That's the approximate change in Z. And from that, we can actually, we'll just stop there. So let's not do example 5. We'll do it at the start of class. It's more complicated, and these numbers don't turn out nicely without a calculator. I really don't feel like pulling up a calculator. So we'll do this one in class, but that's all. See y'all in class.